Hello everybody, welcome to Mathematics for Programming course. In this video, I'm going to discuss the use of probability for computer programming. So what is probability? Probability is actually a fundamental mathematical concept that plays a crucial role in computer programming. We can use it to help us do modeling of uncertainty. We can use it to make predictions. We can use it to optimize decisions and handle random processes. That's why in our daily life, we rely very much on probability to write programs to model these things. So in this video, I'm going to discuss a number of topics about probability. So let us go to the first section called Basic Probability Concepts. So what is probability? In essence, it is a mathematical tool to measure the likelihood of an event occurring, and the value of the probability would range from 0 to 1. If the probability is 0, it means that it is impossible for the event to happen. If it is equal to 1, it means that it is always possible for the event to happen. And the key ideas of probability would include the sample space, which means all the possible outcomes that you can think about or that can occur. And the events here means the subset of the outcomes. That means out of sample space, what are the events that you are talking about or that you want to happen? And we also need the probability rules, like the addition rule for mutually exclusive events and multiplication for the independent events. We will go over them later. And the most important formula for probability is this one. It is actually a fraction. The number of favorable outcomes divided by the total number of possible outcomes. If we're able to count the numerator and the denominator correctly, it is possible for us to get the probability easily. So let us see a simple example of the probability. Suppose we have a bag with 3 red candies, 2 blue candies, and 5 green candies. So what is the probability of picking a blue candy out of these 10 candies in a bag? Let us go back to the definition here. Number of favorable outcomes divided by the total number of possible outcomes. So the number of possible outcomes is just 10 because we have 10 candies in a bag. And the number of favorable outcomes is 2 because it means that we are talking about the 2 blue candies here. So if I apply the probability formula, I'm able to get 2 over 10, which is equal to 1 over 5 or 0.2 or 20%. So you can use a fraction, that's one number, and the percentage to describe the probability. All these 3 formats are allowed, okay? And let us talk about another rule of probability called the rule of complement. So if something either happens or doesn't happen, the probability of all these 2 things would be 1. I mean, the total probability would be 1. So the probability of the event, which is not A here, is equal to 1 minus the probability of A occurring, okay? 1 minus the probability of A occurring, okay? So that is the complement rule. It means that P of A plus P of not A equals 1, okay? And let us see this example here. If the chance of having a rain tomorrow is 0.3, then the chance of no rain tomorrow would be just 1 minus 0.3, which is equal to 0.7. So that is the application of the rule of complement here, okay? And let us talk about the addition rule. What is the addition rule in probability? If we want to know the chance of either event A or event B happening, and they cannot happen at the same time, we can use the addition rule. So we can have this formula here. P of A or B equals P of A plus P of B, okay? So we can see that if event A and event B cannot happen together, we just add the individual probabilities to get the probability of either A or B occurring, okay? So this condition is important. They cannot happen at the same time. If we can make sure that A and B won't happen at the same time, we can use this formula directly. So let us see this example here. Suppose we are rolling a die, and what is the chance of getting 2 or 5 out of this die? So here, 2 and 5 cannot occur together because we can just have either 2 or 5 when we roll a die, okay? So these two events will not have any overlapping, okay? So in this case, we can say that the probability of getting a 2 is 1 over 6 because we have one face having 2 out of all the 6 faces of a die. So we have 1 over 6 for getting a 2. By the same token, we have a probability of 1 over 6 again for getting a number 5 out of all the faces of a die, okay? So it means that the probability of 2 or 5 is just equal to 1 over 6 plus 1 over 6, which is equal to 2 over 6, or it is able to be simplified to become 1 over 3, okay? So this is the meaning of the addition rule. When the two events do not have any overlapping, we can add the individual probabilities together, okay? Now let us talk about the multiplication rule. If you want to know the chance of both events A and event B happening and they are independent, we can use the formula. So if we are able to show that event A and event B are independent of each other, the probability of both things occurring together would be just the product of the individual probabilities, okay? P of A times P of B equals P of A and B, okay? So let us see this example here. Suppose I flip a coin and roll a die at the same time, okay? So what would be the chance of getting a head and a 6? So as we know, when we flip a coin and roll a die, the outcome from a coin isn't able to affect the outcome of a die. So if we have this idea in our mind, we can say that the two events, flipping a coin and rolling a die, will be independent of each other. So if we know that the two events are independent of each other, and if we want to find out the probability of both things occurring together, I just need to apply the multiplication rule here to do P of head and 6 equals 1 over 2 times 1 over 6, which is equal to 1 over 12. So to get a head, we have one head out of two faces of a coin, okay? And to get a 6, we have 1 6 out of the 6 faces of a die. That's why we have 1 over 2 and 1 over 6 as the individual probabilities, okay? So how can we apply probability in programming? We can use it to generate random events in computer games, for example, the simple dice rolls in simulations. Or we can need it to handle the load balancing in distributed system, because the routing of the distributed systems is probabilistic, okay? That means which route to choose is having some kind of random pattern, okay? And we can also use probability to handle errors in algorithms. For example, we have some algorithms like this one, randomized quick sort for average case efficiency. So we have the randomized feature in the algorithm. That's why we can use probability to control the randomness of the algorithm, okay? And of course, we can also use probability to handle cryptography. For example, when we want to generate a key randomly, we can use the random key generation approach by considering the key in the probabilistic sense. Okay, so let us see the Python code to estimate the number of heads in n tosses. So here I have the program in Python. Before I do so, I have to import the random module so that I'm able to pick up values randomly with this module. Okay, so I write a function called simulate coin flips, and I want to simulate the coin flips for 1000 times. That means I have the number of flips as 1000. That will be the argument of this function. Okay, so I want to count the number of heads out of 1000 simulations. That's why I have to set the number of heads at 0 at the beginning. Okay, and for the range in n number of flips, that means from 0 to 1000, excluding the final value of the input argument, I need to do the content inside the for loop for 1000 times, okay? So random.choice here is the function that allows us to pick up heads or tails randomly, okay? So I need to do the random choice function for 1000 times, and out of the 1000 times of random choices, there can be some heads or there can be some tails coming from this function. So I just count the number of heads obtained from each of the function call of the random.choice function, okay? So if I get a head, it means that I'm able to add the head count by 1. And then after finishing the entire for loop, I find out the probability as the number of head counts divided by the number of flips. So it is just consistent with the definition of probability by doing the division of the number of favorable outcomes by the number of possible outcomes. Okay, and then I just return the probability value. So since a coin has two sides, and if we assume that the coin is fair, it means that the probability of getting a head and the probability of getting a tail would both be 0.5. So for 1000 times, you may assume that the probability of getting 500 heads would be equal to the probability of getting 500 tails, theoretically. But in simulation, there can be some random effect. So it is possible that the probability will not be exactly equal to 0.5. So let us see the result of the simulation. Yes, you can see that I'm able to get 0.485, which is a value a bit close to 0.5. So it means that I have 485 heads out of 1000 tosses. Okay. So it means that we are able to do the simulation of the coin tossing. Okay. Now let us talk about another topic of probability, which is the random variables and probability distributions. So what is a random variable? A random variable can help us assign a numerical value to each outcome in a sample space. This sentence is a bit abstract, but when we see an example, the meaning of the random variable will be quite clear. So let us go to this example. We can flip a coin for 3 times, and then we can let x be the number of heads out of the 3 flips. Okay. So the number of heads from 3 tosses can be 0 heads, 1 head, 2 heads, or 3 heads. Okay. So these are the possible values of x here. So x here is our random variable, which means the number of heads out of the 3 tosses. Okay. So for random variables, it can be further classified into 2 types. We have the discrete random variable and the continuous random variable. So what is a discrete random variable? This discrete random variable would take countable values. So the random variable will be just 0, 1, 2, and so on. So for example, the number of goals in a soccer game can only be integers, or even non-negative integers, 0, 1, 2, and so on. So when we have these random variables, we can say that we are handling a discrete random variable. Okay. Another case is the continuous random variable. It can take any value in a range, including decimals. So if the random variable consists of some continuous values, we are doing a continuous random variable. So for example, if we want to record the time it takes to run a race, the time can usually be a decimal number. So I can say 12.3 seconds, okay? And for this continuous random variable, we can also allow something like 12.37 or even 12.376. So the numbers to be contained in a continuous random variable can be just any real number in a given range, okay? So for this situation, we have the continuous random variable. And let us talk about another term called distributions, which is quite related to the random variable. So a distribution would describe how the probabilities are spread. The distribution can be discrete if we talk about countable outcomes. If we talk about uncountable outcomes, the distribution would be a continuous one, okay? So for the discrete one, we have different distributions. For example, we have the binomial distribution and the Poisson distribution to handle the continuous distribution. And for uncountable ones, we can have normal distribution or uniform distribution to handle or to tackle the continuous distributions, okay? So let us see here. There are 2 types of probability distributions. The discrete one here, this uses a probability mass function, PMF. So we can make a PMF to describe the discrete probability distribution, okay? The probability that the random variable equals x is known as Px equals x, okay? So this is the capital X and this is the small letter x. So this is the random variable and this x is really a particular value of the random variables, okay? So let us see the following example about the probability mass function. So if we roll a die we can possibly have 1, 2, 3, 4, 5, or 6 to come up. And if we let x be the number rolled out, it means that this x can be 1, 2, 3, 4, 5, or 6, okay? So each number also has an equal chance, right? It means that the probability distribution would be like this one. For all the possible outcomes, x equals 1, x equals 2, up to x equals 6, all the probabilities would be just 1 over 6, okay? So that is the discrete probability distribution of rolling a die, okay? And we can see that all the probabilities must add up to 1, such that the probability of getting a 1 plus the probability of getting a 2 plus the probability of getting a 3, 4, 5, or 6 would be 1, okay? So we can always check this condition when we are given a discrete probability distribution, okay? Now, let's talk about continuous probability distribution. In this distribution, we use a probability density function called PDF. And if we use the PDF, we don't need to find the probability of an exact random variable. Instead, we can find the probability of a continuous range. So how can we apply the continuous range to the probability? Let's see the evaluation of the probability below. The probability that a random variable x lies within a and b is equal to the integral of f of x from a to b, which can be interpreted as the area under the curve y equals f of x from x equals a to x equals b. So we can use an integration to denote the probability of a continuous random variable. So here f of x is the PDF, which is the continuous function, and the integral here would add up the probabilities in that range. So we can expect that if we consider all the real values of x in the probability, we will have the integral from negative infinity to positive infinity to become 1, which is just the area under the curve equals 1, okay? And let us see the following example. Suppose we want to evaluate the probability of someone to finish a test within some amount of time. So suppose the probability density function PDF is x over 2 for x between 0 and 2 inclusively. And if we have this information, we can find the probability that the time to finish the test is within 0.5 time unit to 1 time unit. Okay, so we just do the integration as here from 0.5 to 1. So after we do the integration, we can use the integration rules to help us get this antiderivative. And then after I put the upper limit and the lower limit into the antiderivative, I'm able to get 3 over 16 as the answer to the integration. And we can really check that whether this f of x is really a valid probability density function. How can we do so? We just integrate this function from negative infinity to positive infinity. So we can see that we will be able to get 1 back, which means that this f of x is really a probability density function because it follows this definition shown here, okay? So how can we apply continuous probability distribution in programming? We can use it to model the user behavior in web analytics. For example, if we have a Poisson distribution, we can use it to account for the number of events that occur in a given amount of time. For example, we can use it to model the distribution of clicks, okay? And we can also use the probability distributions in machine learning. So for example, we can use the normal distribution for feature scaling or the Gaussian processes. And we can also use probability distributions in simulations. For example, we can assume that in Monte Carlo integration, the random sampling can be treated as a uniform distribution. Okay. And for the queuing system in networking, we can use the exponential distribution to model the arrival times of the packets in the network. Okay. So let us see how we can use Python to generate some samples from a normal distribution. So here I have some code snippet here. I need to use NumPy, and I want to use matplotlib.pyplot here to help me do the plotting of the graph as well as getting the random numbers. Okay. So I want to generate 1000 samples from the normal distribution with the mean of the normal distribution as 0 and the standard deviation of the normal distribution as 1. So I can use this line here, np.random.normal, mean as 0, standard deviation as 1, and I want to do the sampling for 1000 times, okay? So I will be able to have an array that stores the result up coming from the random sampling out of a normal distribution with mean equals 0 and standard deviation equals 1, okay? And then I just want to plot the histogram of the values obtained from the normal distributions. I need 30 bins, and I want to show the probability density function so that the area of the graph will be just 1, okay? So I can also find out the mean and the variance of the result sampled, okay? So in principle, the sampled mean here would be close to 0, and the sampled variance would be close to 1 squared, which is just 1. So let us see the result. Yes, you can see this one. The normal distribution obtained from the sampling result would be like a bell, okay? So we have higher probability density in the middle around 0, and we have smaller probability densities for numbers that are quite far away from 0, okay? And when we find out the result of the mean from the samples, we see that the mean would be quite close to 0 theoretically, and the variance would also be a bit close to the theoretical result of 1, which is equal to the standard deviation squared, which means 1 squared, okay? So we can do the normal distribution by using the NumPy feature, okay? Now let us talk about the third part of the video about the expected value and variance. This variance means the expected variance, okay? So the expected value, or what we call the mean, is actually the long-run average value of repetitions of the experiment. That means if we repeat the experiments for many times, what would be the average value to come up? So we can use the formulas about the expected value to see the mean of our result. So we can study the expected values from discrete distributions and continuous distributions differently. But the principle is the same, even though the formulas may be a bit different. So let us talk about the discrete distributions first. For discrete random variables, we have this one. The expected value of this random variable will be just equal to sigma of something, x times p, x equals x, okay? So x times the probability, and I add up all these products, I'm able to get the expected value, okay? So let us see the example here. We can toss a coin twice, and let x be the number of heads. So x can be 0, 1, or 2, because the number of heads can be 0, 1, or 2 when we have only one coin to toss twice, okay? So to get no heads, the probability would be 1 over 4. It comes from 1 over 2 times 1 over 2, because it means that it is the probability of getting 2 tails independently from 2 tosses, okay? And for x equals 1 here, it is 2 over 4, because for one head, it can mean that the first toss is a head and the second toss is a tail. Or it can also mean that the first one is a tail and the second one is a head. So we have 1 over 4 for the first case and 1 over 4 for the second case. Since these two events mentioned, head and tail together with tail and head are mutually exclusive, I can just add the two probabilities together to get 2 over 4, okay? And for x equals 2, the probability is just 1 over 4 because I want to have 2 heads from 2 tosses. That means the first toss is a head and the second toss is also a head. And each of the 2 tosses is independent of each other. That means I want to do 1 over 2 times 1 over 2 to get 1 over 4, okay? So the expected value of the number of tosses would be just this one, x times p of x equals x, added together. So when x is 0, I will have this 0 here. 0 times 1 over 4, which means this probability of x equals 0, plus 1 times the probability of x equals 1, plus 2 times the probability of x equals 2. So when you plug in the numbers into the formula, you will see that the expected number of heads from 2 tosses of a coin would be just 1. So we expect that the answer would be 1. That means out of 2 tosses, I will have 1 head on average. Okay, so that is the meaning of the use of the expected value formula for discrete distributions. Okay. So how about continuous distribution? Let us see here. A continuous distribution has outcomes that can be any number in a given range. So even if the result is a decimal number, it is also allowed. So the formula is the counterpart of the discrete case, okay. Instead of doing addition, we do the integration from negative infinity to positive infinity, okay. And the thing to be integrated is just this one, x times f of x, okay. And the lower limit and the upper limits are usually replaced by the maximum and minimum values of the random variable. So we don't always need to handle infinity symbols all the time, okay. So let us see this example. For example, the time x to finish a quiz is between 10 and 20 minutes. And the PDF, I mean the probability density function of the time to use will be this one. F of x equals 1 over 10 for x between 10 and 20 inclusively, okay. So this one is a uniform distribution. So we have an equal chance for any time between 10 and 20. So you can see that the PDF doesn't depend on x, okay, so we have a uniform distribution. And the expected value of the time used to finish a quiz will be just doing the expectation here, okay. The expected value would be just using the formula shown here, okay. And here, the lower limit is just 10 and the upper limit is just 20 because these two values are already the smallest and the largest number for a given distribution, okay. So I can do the integration here by checking up the integration tables on the web, and then when I do the formula here, I'm able to see that the value will be 15. So it means that the average time to finish the quiz is 15 minutes, okay. So if we have the continuous distribution, I'm able to get the expected value by using the formula shown here, okay. So that is the major idea behind the continuous distribution, okay. And the variance of the expected value will be able to measure the spread of the distribution around the mean. So we can study the variance from the discrete distributions and the continuous distributions too. How can we do so? Let us tackle the discrete distributions first. For discrete random variables, we can use this formula. So I add the terms here. So for each x, I will have one such term here. The whole thing squared multiplied by the corresponding probability, okay? And x here is each of the possible values, and mu here is actually our expected value or average obtained here, okay? And px equals x is just the probability of that value, okay? So let us see the variance of the coin tossing. So we already know that the average number of heads obtained out of 2 tosses of a coin will be 1 over 4, okay? So we know that the expected value of getting 2 heads will be equal to 1, which is already found in the previous part, okay? So the probability of getting no heads will be 1 over 4. The probability of getting 1 head is 2 over 4. And the probability of getting 2 heads will be 1 over 4. And we also know that the expected number of heads would be just 1, okay? So how can we get the variance? We can use the formula directly. So the formula is here. 0, 1, and 2 are put here, okay? And mu here is always 1, which is coming from the expected value of the heads out of 2 tosses, okay? And this probability will be coming from the probabilities shown here, okay? So I can do the plugging in directly to get the answer as 0.5. It means that the variance of the expected number of heads will be 0.5, okay? So how about the continuous distributions? We can also have a formula for the variance of the continuous random variables, which is this one. Instead of using the sigma notation, I use the integral instead, okay? The integral would be from negative infinity to positive infinity, okay? And here, f of x is the probability density function, okay? Mu is again the expected value, okay? So let us see the example here, which is just the previous case. I have an x to be the random variable, which means the time to finish a quiz. And the PDF here is following this one, which is a uniform distribution, okay? And we already know that the expected value of the time will be 50 minutes already from the previous example. And then we can use it to calculate the variance, which is this one. So I can do the integration here. So the variance can be evaluated from this formula. You can always check some integration tables on the web to do the integration. And you will find that the answer would be just 8.33. So that is the variance of the number of minutes to finish a quiz, okay? So the applications of expected values and variances in programming can be something like this one. We can use it to do algorithm analysis. That means we can find the expected runtime in randomized algorithms, like the skip lists, okay? And we can also use them to do financial modeling. We can use them to find out the expected returns in algorithmic trading, okay? And we can also use them to handle the reinforcement learning. For example, we can find the expected rewards in some policy optimization. We can also use them to handle data compression. For example, the Huffman coding would allow us to evaluate the expected frequencies, okay? So let us see the implementation of the expected values and variance in Python. So here I have 6 possible outcomes to simulate the tossing of a die, okay? And the probability will be just that one. 1/6 for all of these possible outcomes, okay? That's why I would repeat 1/6 for 6 times to get the probability distribution for tossing a die, okay? And the expected value is just that one. I do the summation to this product outcomes times probabilities. So I have 6 outcomes and 6 corresponding probabilities. That's why I would do element-wise multiplication and then I add all the products up to get the expected value. And I'm also able to do the variance by applying the formula like this one. The probabilities times the outcome minus the expected value whole squared, okay? So here we just repeat the formula here. This one, okay? And I'm able to get the variance by using this formula, okay? I sum all these quantities obtained by doing pair-by-pair operation of the outcomes array and the probabilities array, okay? So let us see the result. So you will find this answer. The expected value will be exactly 3.5 and the variance will be something like this one, 2.91 something, okay? So you will see that we are able to evaluate the expected value and the variance by using NumPy as well, okay? Okay, let us talk about the next topic about conditional probability. The conditional probability is actually the probability of an event given another event has occurred. So the important word is here, given, okay? So the conditional probability helps us to make smarter guesses when we know part of the story. So if we have something in our mind saying that we have some probability given beforehand, we can use this given probability to make a smarter guess, okay? So the conditional probability is written as P of A given B here, okay? This vertical line is called given, okay? So it means something like this one here. The probability of event A happening given that event B has already happened, okay? So that's why we will say given B here, okay? And the formula of the conditional probability is this one. P A given B equals P of A intersect B divided by P of B, okay? So P of A intersect B is the probability that both A and B would happen. That's why we will have an intersection of the two sets A and B. And P of B here means the probability that B would happen, okay? So if we know B, we can use it to make a smarter guess of the event of A coming out, okay? So let us see the example here. Suppose we have a bag. The bag has 3 types of things. 3 red candies, 2 blue candies, and 5 green candies. Okay, so altogether we have 10 candies. So what would be the probability that a candy is red given that it is not green? So if we know that the candy is not green. It is possible that it is red or blue according to the setting in this question, right? So we have to find out the total number of non-green candies first. So we have 3 red and 2 blue. That's why we have 5 non-green candies, okay? And we can also need to find out the number of red candies among the non-green candies. So we have 3 red candies out of the 5 non-green candies, okay? And then we can apply the formula directly. Probability of red given not green is just equal to the probability of red and not green divided by the probability of green. So the probability of green is just 5/10, and the probability of red and non-green is just 3 out of 10. So we have 10 candies and 3 of them are red and not green. Okay, that's why we can apply the formula here to see that it is 3/5, which means 0.6 or 60%. Alternatively, we can do the division rather directly by dividing the number of red candies out of the number of non-green candies, okay? So we can also get 3 out of 5, okay, as the answer. So this is an alternative answer by using the number of red candies and the number of non-green candies directly, okay? So this answer here would be like 3/10 divided by 5/10. But we can also use the number directly, okay? So let us go to the implementation of conditional probability in Python. So this is a simple example here. So we have some users and they have their ages and whether or not they have already clicked on a web page, okay? So we need to find out the teenager first. So we can check the age of the users to see how many teenagers are there. The teenagers would be defined as the people of age between 13 and 19 inclusively, okay? And then I can filter the users who are teens from the users list, okay? So I want to find out the user whose age is not regarded as a teen, okay? So I can use this list comprehension to help us get the teen users. And I can just get the number of teens by counting the number of elements in this teens user. That's why I have the number of teens here. And I want to see how many teen users really clicked the ad. So I want to go to the teens users that we already filtered. And then I would like to check these teen users who really clicked the web page, okay? So teens clicks here means the users that are teenagers as well as having clicked the web page, okay? And the number of teens with clicks is just equal to the length of this list, okay? So I can find out the conditional probability as here. If I want to find out the probability of clicking a web page given the user is a teenager, I'm able to use the formula here, the number of teen clicks divided by the number of teens. So I'm able to find out the number of teens first, and I'm able to find out the number of teens who really clicked the web page. And then I do the division directly to finish the conditional probability, okay? So let us see the result. Okay, you can see 0.75. It means that for the teens that are really treated as teenagers, I have how many of them? Let me check. 1, 2, 3, and 4. I have 4 of them. And from these 4 teenagers, how many of them have really clicked the web page? Let me see. 1, 2, 3. Okay. So out of the 4 teenagers, 3 of them really clicked the web page. That's why I'm able to do the conditional probability in this way, by dividing the number of teens who really clicked the web page by the number of teens actually, okay? So this is just similar to the numerical example here by doing the division of the numbers directly here, okay? So we have really got some teens. That's why I would go to the if part rather than the else part, okay? So this video has discussed many things about probability for computer programming. I told you the basic probability concepts by using the number of favorable outcomes divided by the total number of possible outcomes to get the probability. I also told you the addition rule, multiplication rule of probability. I also told the random variables and the probability distributions, and we can handle the discrete one and the continuous one. Okay. We also know how to get the expected value of a probability distribution and the corresponding variance of a probability distribution. And the probability distributions can be discrete or continuous. We also know how to calculate conditional probability by using this formula. This is the end of the video. If you have any questions about my video, please leave your questions on the comment section below the video. If you like this video, please give me a like and please subscribe to my channel. Thank you for watching.